Satellite motion. Objective: satellite motion. Explain how the speed of a satellite in circular orbit around Earth is related to the distance an object falls in the first second due to gravity. Describe the motion of a satellite in a circular orbit. Describe the shape of the path of a satellite in an orbit around Earth. Apply the energy conservation law to describe changes in PE and KE of a satellite in different portions of an elliptical orbit. State Kepler's 3 laws of planetary motion. Determine the speed, the vertical speed, required to ensure a projectile can escape Earth. Big idea. The path an Earth satellite follows the curvature of the Earth. If you drop a stone, it will fall in a straight line path to the ground below. If you move your hand horizontally as you drop the stone, it will follow a curved path to the ground. If you move your hand faster, the stone will land farther away and the curvature of the path will be less pronounced. What would happen if the curvature of the path matched the curvature of the Earth? The answer is simple enough. Without air resistance, you'd have an Earth satellite. That's a picture of the International Space Station. Beautiful. What happens when you disturb the path of a pendulum? Make a pendulum from a mass and a 1 meter long string. Tie the free end of the string to a support. Set the pendulum swinging. It should move back and forth only and not side to side. While the pendulum is swinging back and forth, tap the mass sideways. Repeat step 3 several times, each time tapping the mass with a different force. Observing, describe the original shape of the path of the mass. Drawing conclusions. What effect does tapping the mass with different forces have on the shape of the path? Predicting, how might changing the amount of mass affect the nature of the path? 14.1 Earth satellites. Simply put, an Earth satellite is a projectile moving fast enough to fall continuously around Earth rather than into it. Imagine yourself on a planet that is smaller than Earth, as shown in figure 14.2. Because of the planet's small size and low mass, you would not have to throw the stone very fast to make its curved path match the surface curvature of the planet. If you threw the stone just right, it would follow a curved orbit. How fast would the stone have to be thrown horizontally for it to orbit Earth? The answer depends on the rate at which the stone falls and the rate at which Earth curves. And the air resistance too, I would imagine. Figure 14.1. The greater the stone's horizontal motion when released, the wider the arc of its curved path. Next is 14.2. If you toss the stone horizontally with the proper speed, its path will match the surface curvature of the small planets. Recall from Chapter 4 that a stone dropped from rest accelerates downward or towards the center of Earth at 10 meters per second squared and falls a vertical distance of 5 meters during the first second. Also recall from Chapter 5 that the same is true of any projectile as it starts to fall. Recall that in the first second, a projectile will fall a vertical distance of 5 meters below the straight line path it would have taken without gravity, as shown in figure 14.3. It may be helpful to refresh your memory and review figure 15.11. A geometric fact about the curvature of our Earth is that its surface drops a vertical distance of nearly 5 meters for every 8,000 meters tangent to its surface, as shown in figure 14.4. Figure 14.3, throw a stone at any speed, and 1 second later, it will have fallen 5 meters below where it would have been without gravity. Study the figure carefully. Figure 14.4, in the curvature of Earth, the surface drops a vertical distance of nearly 5 meters for every 8,000 meters tangent to its surface. A stone thrown fast enough to go a horizontal distance of 8,000 meters during the time of 1 second it takes to fall 5 meters will orbit Earth. Isn't this speed simply 8,000 meters per second? So we see that the orbital speed for close orbit about Earth is 8,000 meters per second, or 8 kilometers per second. A stone thrown fast enough to go a horizontal distance of 8,000 meters. At that speed, atmospheric friction would burn an object to a crisp. That's why a satellite must stay about 150 kilometers or more above the Earth's surface to keep it from burning due to the friction of the atmosphere. The 5-meter drop for every 8,000 meter tangent means that if you were floating in a calm ocean, you'd be able to see only the top of a 5-meter mast on a boat 8,000 meters away. Concept check. Near the surface of Earth, how fast does a stone have to be thrown to orbit Earth? 14.2. Mass resists acceleration. Interestingly, in circular orbit, the speed of a circling satellite is not changed by gravity. We can understand this by comparing a satellite in circular orbit to a bowling ball rolling along a bowling alley, as shown in figure 14.5. Why doesn't the gravity that acts on the bowling ball change its speed? The answer is that gravity is pulling neither forward nor backward. It pulls straight downward, perpendicular to the ball's motion. The bowling ball has no component of gravitational force along the direction of the alley. The same is true for a satellite in circular orbit. Here, a satellite is always moving at a right angle perpendicular to the force of gravity. Figure 14.5. The speed of the bowling ball and the satellite are not affected by the force of gravity because there is no horizontal component of the gravitational force. It doesn't move in the direction of gravity, which would increase its speed, nor does it move in the direction against gravity, which would decrease its speed. Instead, the satellite exactly crisscrosses gravity so that no change in speed occurs, only a change in direction. A satellite in circular orbit around Earth is always moving perpendicular to gravity and parallel to Earth's surface at constant speed. Think, satellites in close orbit fall about 5 meters during each second of orbit. How can this be if the satellite does not get closer to Earth? In each second the satellite falls about 5 meters below the straight line tangent it would have taken if there were no gravity. Earth's surface curves 5 meters below an 8-kilometer straight line tangent. Since the satellite moves 8 kilometers per second, it falls at the same rate. Earth curves. For a satellite close to Earth, the time for a complete orbit around Earth, its period, is about 90 minutes. For higher altitudes, the orbital speed is less and the period is longer. Communication satellites are located in an orbit 6.5 Earth radii from Earth's center, so that their period is 24 hours. This period matches Earth's daily rotation. They are launched to orbit in the plane of Earth's equator, so they are always above the same place on the equator. The moon is farther away and has a 27.3-day period. The higher the orbit of a satellite, the slower its speed and the longer its period. The International Space Station, shown in Figure 14.6, orbits at 360 kilometers above Earth's surface. Like all satellites, tangential velocity assures that it falls around Earth rather than into it. The ISS and its inhabitants circle 360 kilometers above the Earth, well above its atmosphere, in a state of continual free fall. Acceleration toward Earth is somewhat less than 1g because of altitude. This acceleration, however, is not sensed by the astronauts. Relative to the station, they experience 0g. Over extended periods of time, this causes loss of muscle strength and their detrimental changes in the body. Future space travelers, however, can avoid this when space stations rotate. Recall our discussion of rotating space habitats in Chapter 12. Rotation effectively supplies a support force and can nicely provide Earth normal weight. Recall from Chapter 13 that Isaac Newton understood satellite motion from his investigation of the moon's motion. He thought about the launching of artificial satellites, for he reasoned that without air resistance, a cannonball could circle Earth and coast indefinitely if it had sufficient speed. As Figure 14.7 demonstrates, he calculated the speed to be the same as 8 kilometers per second. When a spacecraft enters the atmosphere at too steep an angle, more than about 6 degrees, it can burn up. If it comes in too shallow, it could bounce back into space like a pebble skipped across water. Let's look at the figure, and it says 14.7, a satellite in circular orbit close to Earth moves tangentially at 8 kilometers per second. Each second it falls 5 meters beneath each successive 8-kilometer tangent. Since such speed was impossible then, he was not optimistic about people launching satellites. What Newton did not consider was multi-stage rockets. The idea of rockets carried piggyback style on other rockets to reach orbital speed by a succession of rocket firings. Describe the motion of a satellite in relation to Earth's surface and gravity. 14.3 Elliptical orbits. A satellite in orbit around Earth traces an oval-shaped path called an ellipse. An ellipse is the closed path taken by a point that moves in such a way that the sum of its distances from two fixed points is constant. The two fixed points in an ellipse are called foci. For a satellite orbiting a planet, the center of the planet is at one focus, and the other focus could be inside or outside the planet. An ellipse can be easily constructed by using a pair of tacks, one at each focus, a loop of string, and a pencil as shown in Figure 14.8. Here's Figure 14.8. A simple method of constructing an ellipse is shown here. Practice this on your own and see if you can actually draw an ellipse. How to draw different ellipses. 1. Draw an ellipse with a loop of string, 2 tacks, and a pen or a pencil as shown in figure 14.8. 2. Try different tack spaces for a variety of ellipses. Or draw an ellipse by tracing the edge of a shadow cast by a circular disc on a flat surface. Think, how can you move the disc to get different ellipses? The closer the tacks, the closer the ellipse is to a circle. When the foci are together, the ellipse is a circle. A circle is a special case of an ellipse. Satellite speed, which is constant in a circular orbit, varies in an elliptical orbit. When the initial speed is more than 8 kilometers per second, the satellite overshoots a circular path and moves away from Earth against the force of gravity. It therefore loses speed. Like a rock thrown into the air, the satellite slows to a point where it no longer recedes and begins falling back towards Earth. The speed lost in receding is regained as it falls back. The satellite then rejoins its path with the same speed it had initially. The procedure repeats over and over, and an ellipse is traced, each cycle as shown in figure 14.9. Figure 14.9, a satellite moves in an elliptical orbit. A. When the satellite exceeds 8 kilometers per second, it overshoots a circle. B. At its maximum separation, it starts to come back towards Earth. And C. The cycle repeats itself. Think. The orbit of a satellite is shown in a sketch. In which of the positions A through D does the satellite have the greatest speed? The least speed. The satellite has its greatest speed as it whips around A. It has its least speed at C. Beyond C, it gains speed as it falls back to A to repeat its cycle. Quite interestingly, the apparently parabolic paths of projectiles such as cannonballs are actually tiny segments of a thin ellipse that extends within and just beyond the center of Earth. Figure 14.10 shows that for speeds less than orbital speeds, the center of Earth is the far focus of the elliptical path. In this case, the near focus is close to the launching site and varies for different speeds. When the projectile traces a circular orbit, both foci are together at Earth's surface. For elliptical orbits, the near focus is Earth's center, and the location of the far focus varies for different speeds. What is the shape of the path of the satellite in an orbit around Earth? Figure 14.10. The parabolic paths of the projectiles are actually segments of ellipses. A. For relatively low speeds, the center of Earth is the far focus. For greater speeds, the near focus is Earth's center. 14.4. Energy conservation and satellite motion. Recall from Chapter 9 that moving objects have kinetic energy. An object above Earth's surface has potential energy due to its position. Everywhere in its orbit, a satellite has both kinetic energy and potential energy. The sum of the Ke and Pe of a satellite is constant at all points along an orbit. In circular orbit, the distance between the planet's center and the satellite center is constant, as shown in figure 14.11. This means that the PE of the satellite is the same everywhere in orbit. So by the law of conservation of energy, the KE is also constant. Thus, the speed is constant in any circular orbit. In an elliptical orbit, the situation is different. Both speed and distance vary. Figure 1411. For a satellite in circular orbit, no component of force acts along the direction of motion. The speed, and thus the kinetic energy, cannot change. Consider this figure 1411 carefully. Satellite design engineer, physics on the job. Satellites play an important role in conducting scientific research, obtaining environmental data, and providing communication services. Satellite design engineers are employed by the United States government through NASA and by commercial communications companies. The goal of a satellite design engineer is to design satellites that will orbit at specific distances from Earth, carry the necessary equipment, and withstand the conditions to which they will be exposed. All of this within a controlled monetary budget. Figure 1412. For a satellite in circular orbit, no component of force acts along the direction of motion. The speed, and thus the kinetic energy, cannot change. Here are two vocabulary words: apogee and perigee. The apogee is the point in a satellite's orbit farthest from the center of Earth. The perigee is the point in a satellite's orbit closest to the center of Earth. The PE is greatest when the satellite is at the apogee and least when the satellite is at the perigee. Correspondingly, the KE will be least when the PE is most, and the KE will be most when the PE is least. As figure 1412 shows, at every point in the orbit, the sum of the KE and PE is constant. At all points on the orbit, except at the apogee and perigee, there is a component of gravitational force parallel to the direction of satellite motion, as figure 1413 shows. Figure 1413. In an elliptical orbit, a component of force exists along the direction of the satellite's motion. This component changes the speed and thus the kinetic energy. This component of force does work on the satellite. Study that very carefully. This component changes the speed of the satellite, or we can say this component of F times the change in distance equals the change in kinetic energy. Either way we look at it, when the satellite gains altitude and moves against this component, its speed and kinetic energy decrease. The decrease continues to the apogee. Once past the apogee, the satellite moves in the same direction as the component, and the speed of the kinetic energy increase. The increase continues until the satellite whips past the perigee and repeats the cycle. Concept check. What is the relationship between the kinetic energy and potential energy of a satellite in motion? Consider this question very carefully. And let's begin the next section. 14.5. Kepler's laws of planetary motion. Newton's law of gravitation was preceded by Kepler's law of planetary motion. Kepler's laws of planetary motion are three important discoveries about planetary motion that were made by the German astronomer Johann Kepler in the beginning of the 1600s. Kepler's career as an astronomer began with a junior assistantship with the famed Danish astronomer Tycho Brahe. Brahe headed the world's first great observatory in Denmark, just prior to the event of the telescope. Using huge brass protractor-like instruments called quadrants, Brahe measured the position of planets over 20 years so accurately that his measurements are still valid today. Tycho Brahe. Figure 1414a, Tycho Brahe, 1546 to 1601, measured the positions of planets over 20 years so accurately that his measurements are still valid today. B. Johann Kepler, 1571 to 1630, devoted many years of his life to the analysis of Brahe's measurements. Two giants in astronomy. Brahe entrusted his data to Kepler. After Brahe's death, Kepler devoted many years of his life to the analysis of Brahe's measurements. Kepler's first law. Kepler's expectation that the planets would move in perfect circles around the sun was shattered after years of effort. He found the path to be ellipses. Kepler's first law states that the path of each planet around the sun is an ellipse with the sun at one focus. Think. The orbital path of a satellite is shown below. In which positions, A through D, does the satellite have the most kinetic energy, most potential energy, most total energy? The KE is maximum at A, the PE is maximum at C. The total energy is the same anywhere in the orbit. Kepler's second law. Kepler also found that the planets do not go around the sun at a uniform speed, but move faster when they are near the sun and more slowly when they are farther from the sun. They accomplished this in such a way that an imaginary line or spoke joining the sun and the planets sweep out equal areas of space in equal intervals of time. The triangular-shaped areas sweep out during a month when a planet is orbiting far from the sun, and when a planet is orbiting closer to the sun, are shown in figure 1415. These two areas are equal. Notes. Kepler's second law is a consequence of the conservation of angular momentum. And his third law is the result of equating Newton's law of gravitation to centripetal force. Figure 1415. Equal areas of space are swept out in equal intervals of time. Kepler's third law is derived from equating centripetal force with gravitational force. So I did that on the upper left, and then I came down and said r cubed over t squared equals gm over 4 pi squared. And this is a constant, because the ratio r cubed over t squared is a constant. The ratio is the same for any distances from mass m. This, in fact, is how the mass of a planet m is made. Simply measure r cubed over t squared and calculate m. Kepler's second law states that each planet moves so that an imaginary line drawn from the sun to any planet sweeps out equal areas of space in equal intervals of time. Kepler was the first to coin the word satellite. He had no clear idea why the planets moved as he discovered. He lacked a conceptual model. Kepler didn't see that a satellite is simply a projectile under the influence of gravitational force directed towards the body around which the satellite orbits. You know that if you toss a rock upward, it goes slower the higher it rises because it's going against Earth's gravity. And you know that when it returns, it's going with gravity and its speed increases. Kepler never realized that a satellite behaves in the same way. Going away from the sun, it slows down. Returning towards the sun, it speeds up. A satellite, whether a planet orbiting the sun or one of today's satellites orbiting Earth, is slowed going against the gravitational field and sped up going with the gravitational field. Kepler wasn't aware of this simplicity and instead fabricated complex systems of geometrical figures to find sense in his discoveries. These proved futile. Kepler's third law. After 10 years of searching by trial and error for a connection between the time it takes a planet to orbit the Sun and its distance from the Sun, Kepler discovered a third law. From Brahe's data, Kepler found that the square of any planet's period is directly proportional to the cube of its average orbital radius. Kepler's third law states that the square of the orbital period of a planet is directly proportional to the cube of the average distance of the planet from the Sun. The mass of any celestial body can be found if it has one or more satellites, for the body's mass is directly proportional to r cubed over t squared. This means that the ratio t squared over r cubed is the same for all planets. So if a planet's period is known, its average orbital radial distance is easily calculated, or vice versa. Kepler's laws apply not only to planets, but also to moons or any satellite in orbit around any body. The elliptical orbits of the planets are very nearly circular. Only the precise measurements of Brahe showed the slight differences. It is interesting to note that Kepler was familiar with Galileo's concepts of inertia and accelerated motion, but he failed to apply them to his own work. Like Aristotle, he thought that the force on a moving body would be in the same direction as the body's motion. Kepler never appreciated the concept of inertia. Galileo, on the other hand, never appreciated Kepler's work and held to his conviction that the planets move in circles. Further understanding of planetary motion required someone who could integrate the findings of these two great scientists. The rest is history, for as we have seen, this task was later taken up by Isaac Newton. Concept check. What are Kepler's three laws of planetary motion? 14.6. Escape speed. When a payload is put into Earth's orbit by a rocket, the speed and direction of the rocket are very important. For example, what would have happened if a rocket were launched vertically and quickly achieved the speed of 8 kilometers per second? Everyone had better get out of the way because it would soon come crashing back at 8 kilometers per second. As figure 14.16 shows, to achieve orbit, the payload must be launched horizontally at 8 kilometers per second, once above air resistance. Launched vertically, the old saying, what goes up must come down, becomes a sad fact of life. 14.16. The initial thrust of the rocket lifts is vertical. Another thrust tips it from its vertical course. When it is moving horizontally, it is boosted to the required speed for orbit. Earth. But isn't there some vertical speed that is sufficient to ensure that what goes up will escape and not come down? The answer is yes. Neglecting air resistance, fire anything at a speed greater than 11.2 kilometers per second, and it will leave Earth, going more and more slowly, but never stopping. Let's look at this from an energy point of view. How much work is required to move a payload against the force of Earth's gravity to a distance very, very far, infinitely far away? The potential energy is not infinite because the distance is infinite, but gravity diminishes rapidly with distance via the inverse square law. Most of the work done in launching a rocket, for example, occurs near Earth. It turns out that the value of PE for a 1 kilogram mass infinitely far away is 62 million joules, MJ. So to put a payload infinitely far from Earth's surface requires at least 62 MJ of energy per kilogram of payload. A KE per unit mass of 62 MJ per kg corresponds to a speed of 11.2 kilometers per second. This is the value of the escape speed from the surface of Earth. The escape speed is the minimum speed necessary for an object to escape permanently from a gravitational field that holds it. The mind that encompasses the universe is as marvelous as the universe that encompasses the mind. If we give a payload any more energy than 62 mj per kg at the surface of Earth, or equivalently any greater speed than 11.2 kilometers per second, then, neglecting air resistance, the payload will escape from Earth, never to return. As it continues outward, its potential energy increases and its kinetic energy decreases. Its speed becomes less and less, though it is never reduced to zero. The payload outruns the gravity of Earth. It escapes. The solar system. The escape speeds of various bodies in the solar system are shown in Table 14.1. Note that the escape speeds from the Sun is 620 kilometers per second at the surface of the Sun. Even at a distance equaling that of Earth's orbit, the escape speed from the Sun is 42.2 kilometers per second. The escape speed values in the table ignore the forces exerted by other bodies. A projectile fired from Earth at 11.2 kilometers per second, for example, escapes Earth, but not necessarily the Moon, and certainly not the Sun. The first probe to escape the solar system, Pioneer 10, shown in figure 1417, was launched from Earth in 1972 with a speed of only 15 kilometers per second. The escape was accomplished by directing the probe into the path of oncoming Jupiter. It was whipped about by Jupiter's great gravitational field, picking up speed in the process, just as the speed of a ball encountering an oncoming bat is increased when it departs from the bat. Its speed of departure from Jupiter was increased enough to exceed the Sun's escape speed at the distance of Jupiter. Pioneer 10 passed the orbit of Pluto in 1984. Unless it collides with another body, it will continue indefinitely through interstellar space. Figure 1417, Pioneer 10 launched from Earth in 1972, escaped from the solar system in 1984, and is wandering in interstellar space. These are some pictures taken by the satellite. And some artistic rendering as well. Like a note in a bottle cast into the sea, Pioneer 10 contains information about Earth that might be of interest to extraterrestrials in hopes that it will one day wash up and be found on some distant seashore. It is important to point out that the escape speeds for different bodies refer to the initial speed given by a brief thrust, after which there is no force to assist motion. But we could escape Earth at any sustained speed greater than zero given enough time. Suppose a rocket is going to a destination such as the Moon. If the rocket engines burn out while still close to Earth, the rocket will need a minimum speed of 11.2 kilometers per second. But if the rocket engines can be sustained for a long period of time, the rocket could go to the Moon without ever attaining 11.2 kilometers per second. It is interesting to note that the accuracy with which an unpiloted rocket reaches its destination is accomplished not by staying on a pre-planned orbit or by getting back on the path if it strays off course. No attempt is made to return the rocket to its planned path. Instead, by communication with the control center, the rocket in effect asks, "Where am I now, and where do I want to go? What is the best way to get there from here, given my present situation?" With the aid of high-speed computers, the answers to these questions are used to find a new path. Corrective thrusters put the rocket on this new path. This process is repeated continuously along the way until the rocket reaches its destination. Is there a lesson to be learned here? Suppose you find in your personal life that you are off course. You may, like the rocket, find it better to take a newer course that leads to your goal as best plotted from your present position and circumstances, rather than try to get back on a course you plotted from the previous position and in perhaps different circumstances. So many ideas in physics, it seems, have a moral. Concept check. What condition is necessary for a payload to escape Earth's gravity? Communications, satellites, science, technology, and society. The electromagnetic signals that are broadcast into space to carry television programs or telephone conversations travel in straight lines. In times past, these straight line, often called line of sight communications, required tall receiving antenna towers and single boosting relay stations on high buildings or mountains. Today, many television and telephone signals bounce to us from satellites. These communication satellites are in equatorial orbits with 24-hour periods. Because they revolve once each time Earth rotates once, they appear stationary when we look up at them. These satellites are said to be in geosynchronous orbits. Dish-shaped antennas almost anywhere on Earth are on a line of sight from one or more communication satellites, because communication satellites are in equatorial orbit. Dish antennas on the equator may tilt east or west, but they don't tilt north or south. An equatorial dish right under the communication satellite is looking straight up. It is held water. It would resemble a bird bath filled to the brim. Antennas north of the equator must be tilted to the south and perhaps east or west too. Those south of the equator must be tilted to the north and likely east or west as well. Unless you live on the equator, all of the antennae that you see look like partly empty bowls. In Antarctica or near the North Pole, a dish antenna is tipped so far over that it could hold no water at all. The fact that geosynchronous satellites remain in one place overhead means it is possible for them to drop vertical cables to Earth's surface where they could be attached. This is a picture of Telstar, the first American communication satellite. Cables composed of very strong and lightweight carbon-based materials are currently being researched. Rather than being rocketed to the satellite, suppliers could be lifted in elevator fashion. Watch for such space elevators in the future. Here's some information on early United States satellites. First U.S. satellite is Explorer 1 in 1958. It was answer to Sputnik, which was a Russian satellite in October of 1957. There were several mission failures, mostly due to rocket malfunctions. The first communication satellite was the Telstar satellite launched by the U.S. in 1962. This marked the beginning of an era. There was an instrumental song in the early 60s called Telstar, and it was a celebration of the launch of the Telstar satellite. Satellite motion summary. A stone thrown fast enough to go a horizontal distance of 8,000 meters during the time 1 second it takes to fall 5 meters will orbit Earth. A satellite in circular orbit around Earth is always moving perpendicular to gravity and parallel to the Earth's surface at constant speed. A satellite in orbit around the Earth traces an oval-shaped path called an ellipse. The sum of Ke and Pe of a satellite is constant at all points along an orbit. Kepler's first law states that the path of each planet around the Sun is an ellipse with the Sun at one focus. Kepler's second law states that each planet moves so that an imaginary line drawn from the Sun to any planet sweeps out equal areas of space in equal intervals of time. Kepler's third law states that the square of the orbital period of a planet is directly proportional to the cube of the average distance of the planet from the Sun. T squared is proportional to r cubed for all planets. If we give a payload any more energy than 62 megajoules per kilogram at the surface of Earth, or equivalently any greater speed than 11.2 kilometers per second, then, neglecting air resistance, the payload will escape from Earth, never to return.